Welcome back to the Cosmic Classroom. We'll now talk about the solar neutrino problem, which is hard to understand because after all, you're not really sure what the neutrino is, let alone the solar neutrino problem. What's the problem? So let me first explain what the problem is. The problem is that when 4 protons fuse to become an atom of helium, as I mentioned before, they will emit gamma rays, they will emit positrons, but they will also emit, as we mentioned before, 2 electron neutrinos. Those are here, 2 electron neutrinos. Those 2 electron neutrinos, we can predict how many of those should be arriving on Earth, we should be detecting on Earth, because we know the rate of fusion in the sun. And the reason why we know the rate of fusion in the sun is because all of the energy that's being generated in the center of the sun eventually leaves the sun on its surface. So we eventually observe that. Then we can count up all that energy, and we know that that energy is coming from fusion. Therefore, we can predict the rate of fusion, how many protons are being combined into helium, how fast. There is a certain number of predicted number density of neutrinos that are then predicted to arrive here on Earth on our observatories. Neutrinos are funny things because they have very small masses. It was actually believed that they didn't even have masses for a while. We now know that they have very small masses. And small, I mean much smaller than an electron, really, really small masses. So they travel very fast, almost at the speed of light. They don't have a charge, so they don't interact electromagnetically with anything else. They travel right through. They travel right through you and me. They travel right through the sun. They travel right through. And it's hard to detect them because they travel right through most things. But every now and then, they interact with matter. So if we understand neutrinos, and if we understand how they interact with matter, we should be able to count them on Earth, take into account that the fact that we just detect a few of them. And this number of detected neutrinos should match with what we expect. Many experiments try to detect those neutrinos, and different experiments got the same result. Always getting just a third of the expected number of neutrinos. As if 2/3 got lost somewhere, or if we don't know fusion. Maybe it's not 2 neutrinos that are formed. Maybe it's less. It's weird. It doesn't match. So for a long time, this is the problem. This was the neutrino problem. If there are so many being created in the sun, why is it that we're detecting only a third of them? The solution to the neutrino problem came when people started to realize that neutrinos actually do have mass, and therefore there are different kinds of neutrinos, slightly different flavors of neutrino. What's created in the fusion is the electron neutrino, but there is also a muon neutrino and a tau neutrino. So there are 3 types, electron neutrino, and I'll put the electron neutrino here. Mu, tau, and electron neutrino. And they change types. They interfere with one another. These particles, they also behave as waves, just like light does. So they have some interference with one another. When they are traveling together, it's like they steal energy from each other. The energy is conserved, but maybe one neutrino will give a little bit of energy to another neutrino, then it will take some energy away. So they can change types. Neutrinos can change types. So the solution to the neutrino problem was to understand that the 3 neutrinos that were emitted, so 3 neutrinos here, for example, that were emitted from the sun. Let's say this is the sun right here. Oh, that's a terrible sun. But this is the sun. It's emitting 3 neutrinos that are then traveling in our direction. Earth is their way. During this trip, they exchange energy with one another. And maybe this electron neutrino here will become a muon neutrino, and maybe this one here will become a tau neutrino, and maybe this one here will continue to be an electron neutrino. And a little bit later, they change energy again. So maybe now this one becomes a tau neutrino, and this one here becomes an electron neutrino, and maybe this one became a mu neutrino. They like changing energy. It's like kids playing together and changing a ball, changing energy. In other words, this starts happening very soon after they are created. They start interfering one another. They start playing ball with one another. By the time they reach Earth, there is only a third of electron neutrinos, because the other third is tau neutrinos and the other third is mu neutrinos. So they are all there. We find them, but they have changed masses. They have changed energy slightly. New detectors are able to detect not only the electron neutrino, but the mu and the tau neutrino. And guess what? They count them all. So now we understand we can account for all the neutrinos, and we know that we know that there is more than one kind of neutrinos. That's the solution for the neutrino problem. Now I have 3 times as many as were detected before, and the problem is solved. Neutrinos change type. They oscillate into different types. And I hope this was helpful to you, and I'll see you in class.